All right, so let's talk about ideal gases and non-ideal gases. So when we say a real gas, we're talking about something that's not an ideal gas. An ideal gas is very close to ideal. So in an ideal gas, we have something that is, the volume of the gas particles are very small. They're insignificant compared to the size of the container. Very small compared to the size of the container. Okay. Now if I have a real gas, it's going to be different than that. So instead of saying it's very small compared to the size of the container, it's not small. Okay, so instead of it being very small, it's not small. In fact, they tend to be rather large particles in general. So its size is significant compared to the size of the container, or at least it's, we could say, more significant compared to the size of the container. The effect of the deviation, so if there's a deviation, the effect is that the observed pressure is going to be greater than the ideal pressure. So the observed pressure, the real pressure, is going to be greater than the pressure that you would expect from an ideal gas because there's less volume, and volume and pressure are inversely related. Intermolecular forces between the gas particles in an ideal gas. We're going to have weak intermolecular forces or negligible intermolecular forces between the gases. In other words, they will be negligible. Almost hardly even worth noticing or worth mentioning. In a real gas, we have stronger IMFs. And what kind of effect would that have on the gas? Well, if we have stronger IMFs, the observed pressure in this case is actually going to be less than the ideal pressure. And the reason is because the intermolecular forces are going to be attracting particles to themselves. As that particle approaches a wall, it slows down and doesn't hit the wall as hard. That reduces the pressure from what you would expect. So it's a lower pressure than expected. Let's talk about temperature, pressure, and volume and the effects that those can have on how ideal how ideal our conditions are. The temperature of the container, if it's a high temperature, that's going to be the most ideal condition, because at a high temperature, particles are moving faster, and since they're moving fast enough that those intermolecular forces don't really make as much of a difference. So you could guess that the non-ideal behavior would come from having a lower temperature. And the effect of the deviation, if you have low temperature, the IMFs have a greater effect in slowing particles before they hit container walls. What about the pressure in the container? Pressure in the container, if it's ideal, is going to be low pressure. And for it to be non-ideal conditions, of course, that would be high pressure. If we have high pressure, the IMFs have greater effect because particles are closer together. That's our reasoning. That would be an unideal situation. And then finally, the volume of the container. If it's a large volume relative to the particles, that's going to be more ideal. The non-ideal condition would be a small volume. And the non-ideal condition would be that the volume of the particles have a greater effect. And we could add to each of these. So if the volume of the particles have a greater effect, then that tells us that the pressure observed is going to be greater than the pressure of the ideal gas. Now, if intermolecular forces are the problem, which is the case with the first two, then the pressure observed is going to be lower than the ideal pressure. And we could say the same thing for this first one. I didn't really save a lot of room to write that, but we can put it right here. Same situation. If the intermolecular forces have a greater effect, then that is going to cause the pressure observed to be lower than the ideal pressure. And that pretty well summarizes, this page pretty well summarizes what we've talked about with non-ideal behavior or deviations from ideal gas law.